ever done. Okay? And if you look up on Wikipedia, for instance, problems in physics, I think it's the first, the vacuum catastrophe, 122 orders of magnitude problem. Well, I solved that in an instant. Sorry, but I did. About a year ago, when I realized, wait, I've got a 10 to the 55th gram proton that is a result of the 10 to the 93 grams per centimeter cube density of the vacuum, okay? And so per proton volume, right? And what happens if I grow that thing to the size of the universe? Obviously, the density is going to drop. So I grew it to the size of the universe, and my result was 10 to the 30th gram, minus 30th gram per centimeter cube, really close to the measured cosmological constant. So I was like, wow, it actually works. And in physics, this would be close enough that you could say, well, I'm going to adjust the size of the universe till I get the right number for the measured value. And that's going to give me a prediction for the size of the universe, right? Which we don't know. There's a wobble between 10 to the minus, 10 to the 27 to 10 to the 29. So 10 to the 28 is usually the value that's given. But it's rough, obviously, because it's cosmological. So I said, well, how can I get a real number? Because I could have adjusted it, but I didn't want to cherry pick. I had been given hell for the last 2 years on the internet, by all my critics saying, he's cherry picking. So in this paper, I was like, no cherry picking. There will be no cherry picking. Forget cherries. And so on. So I said, okay, well, I know the mass of the universe, since this should be accurate. If it's accurate, if I do the Schwarzschild condition of that mass, right? Remember that equation? If I solve that equation, it'll give me a radius for the black hole universe. Let's see if I do the same thing with that radius. This would be the first time we get an exact radius for the universe. So I did that, and when I grew it, boom, 10 to the minus 29 grams per centimeter cube. I was like, okay, this works. This works. And again, if this is correct, this is the first time we know the exact mass and the exact size of our universe. So I said, wow, this is showing so much evidence of the holographic principle of this concept that from studying the proton, I can actually understand the whole universe. I should look at the holographic principle and apply it. The holographic principle in physics is utilized to describe the entropy of black holes. That would be the amount of thermodynamics that come off a black hole. You could think of it in Kelvin. And what is currently used is that they map little Planck's distance on the surface event horizon of the black hole and then count them and make this calculation and they get the entropy of a black hole. I started to think this way. I started to apply that. So I said, okay, it's holographic. Let's look at relationship. I took the Planck's distance. I knew it was I made it a surface, and I plastered it over the surface of the event horizon of the black hole proton. But when I plastered it, I took the surface area of the proton, right? And I divided it by the number, by the area of the Planck's distance little circle. So it has to be space filling. That means the circles cannot be one beside each other like that, because if they were, there would be little spaces in between. It has to be space filling. You guys follow me? So when I said, well, how could they be space filling? Well, guess what I got? The flower of life symbol. And I thought, wow, you know, if it comes out, I'm gonna shit my pants. I almost did. I almost did. Because what I did is I said, okay, how many of those is there? Those are all little Planck's oscillations, right? And there's 10 to the 40th of them. So there's a lot. And I said, okay, out of those, remember in the middle is all the little Planck spheres, right? See, these are little Planck spheres in the middle in 3D that are projecting onto the surface. That is the holographic principle. You guys saw that? Do it again. Okay. That's actually the beginning of the movie Black Hole that Guyam just released about the research I'm doing. So let me try to, oh, I missed it. Let me do it again, just so it's clear. So inside the volume of the little proton, right, is all the Planck spheres, right? That's how I got the 10 to the 55th, right? So this are all the little Planck spheres. Here you see tetrahedrons because they tiled, if they produce the flower of life structure, they tiled just like tetrahedron structures. And that's where the work I'm doing links with the work that Richard Hoagland is doing and others in hyperdimensional physics, because that is the structure of the vacuum, right? And so I said, okay, these spheres are projecting the information of the whole universe onto the surface. So so it's a projection onto the surface, which is the holographic principle. And then we're going to see why the surface has less than the interior in a minute. But you see here, it's projecting onto the surface. That's what I was trying to show here. Okay? And it's a curved surface. It's the surface of the event horizon. So when I did that, then it's slow for most people. I'm going to write here. So what I did is I took the number of little circles on the surface, right? All the circles on the surface. That's 10 to the 40th. Can everybody see this? 10 to the 40th. And then the number inside is 10 to the 55th, right? It's the mass of the universe. Basically, divide the number of little Planck surfaces by the mass of the universe, okay? And what I got was exactly, what I got was exactly R sub S, the Schwarzschild mass. 10 to the 14. 10 to the 14, which is the Schwarzschild equation. I have the Schwarzschild equation here. Gravity outputted completely geometrically. No curvature of space-time, no geodesics, just pixelation of the structure of the vacuum itself. This is quantum gravity that I've been looking for all these years. And the solution is exact, okay? Exact only if the tessellation is space-filling, the flower of life. Under the paw of the foo dogs is a sphere with the flower of life tessellated over the surface. The guardian of the knowledge. Then I said, okay, if this is really cool, if this is true, I should be able to continue to do relationship in there and get all sorts of information about our universe. So I took the number of Planck's surfaces, 10 to the 40th, but this time I divided it by 10 to the minus 39, which is the volume, proton volume. The volume of the proton itself, instead of the number of Plancks in there. And the result was 10 to the 79. And when 10 to the 79 came out, I recognized it right away. I said, oh, this is really close to the estimated amount of particles in the universe. Right? We know there's approximately between 10 to the 78 to 10 to the 80th or 10 to the 81 amount of particles in the universe. And so, if this is true, this would be the first time we have an exact number for the actual amount of particles, right? Well, you can think of like protons, right? Most of the universe is hydrogen atom with one proton, so in general, just protons are counted in our universe. So just you could think of the amount of atoms in the universe, if you'd like. So I thought, well, this would be cool if this is exact. So then I did something a little weird. But, you know, I have those moments. I did something a little weird that I'm going to show you I rectified right after, but it gave me the right answer anyway. But I said, okay, each one of these little circles is like a little micro wormhole connecting all the protons, all the Planck's length in the universe with all the other protons. The reason why I thought that way is because that discrepancy between the standard mass and the Schwarzschild mass, I kept on seeing in my head and in my work, in my philosophy, that it's because you can't just look at the mass of one proton because it's influenced by all the other protons in the universe, right? Remember, it's not isolated. So if it's linked, okay, I said, okay, then I got to divide the Schwarzschild condition by all the other protons to see what would be the influence of a proton on one little Planck's distance. So that's what I did. I divided the number of Planck's distances, right, by the number, I divided the mass, the Schwarzschild mass, by the number